So all we've differentiated so far is functions just in terms of x, really. Okay, so x squared, root x, 1 over x, whatever it is. Okay, that's what we've been differentiating thus far. But obviously we can have different functions. Obviously we've already dealt with different functions. What I'm basically talking about is trig functions. Okay, so we also need to be able to differentiate them. Right, these are actually in your formula sheet, so we don't necessarily need to worry too much about memorizing these. It just helps to know why and where this all comes from. Okay, but more importantly, you need to know how to use them, which we'll get to, because as I say, the actual formulas for differentiating them are in your formula sheet. Okay, so you don't need to memorize these, you just need to remember that they're there. Okay, so anything involving sine x and cos x is what we're going to be differentiating. I've written k sine x and k cos x because it might be kind of a coefficient in front of them. So 2 sine x, 3 cos x, whatever it is. Okay, this is what we're differentiating. We're not going to do tan x. You'll do tan x when you get to advanced higher. So we just need to worry about the sine and the cos. Okay. Right, so to show you where these come from, I'm going to start with a graph of y equals sine x. And what we're basically going to do is I'm going to look at the gradients at these different points. So the gradients of the tangents at these different points. Because obviously we know the derivative relates to that. The derivative is the gradient. So if we can look at the gradient at these different points, then we can hopefully relate that back to the actual derivative, and you'll see a pretty snazzy connection here. Okay, so when x is 0, y equals sine x. On the graph of y equals sine x, the gradient is 1. Okay, when x is 30, the gradient is 0.9. When x is 60, the gradient is 0.5. When x is 90, the gradient of the tangent is 0. And in background again, we get minus 0.5, minus 0.9, and then when we get 180, we get minus 1. And obviously these continue. This is just the first half of the graph of y equals sine x. But what we're going to do is we're going to take these values. Okay, so all I've done here is just got the x coordinates. Okay, so 0, 30, 60, 90, or radians, just to be a bit fancy. Okay, and we've got the gradient of the tangent. 1, 0.9, 0.5, 0, minus 0.5, minus 0.9, and minus 1. Ooh. We're going to take these and we're going to actually graph these. Okay, so we're basically what we're doing here is we're doing the graph of x against dy by dx. Obviously, that was a graph of x against dy by dx. Okay, because sorry, that was the graph of x against y, and y being sine x. Okay, now we're going to do x against dy by dx so that we can find the value of dy by dx. Okay, so if we plot these on a graph, when 0 is 1, when x is 0, sorry, y is 1, or dy by dx in this case, and then we've got a 0 at 30 degrees, we've got 0.9, at 60 degrees, we've got 0.5, at 90 degrees, we've got 0, we've got 120 degrees, minus 0.5, 150 degrees, we've got minus 0.9, and at pi, we've got minus 1. And all that would happen is that these start going back up in the same way, and look at that. Ooh, we have a graph of y equals cos x. Okay, what this is basically saying is that the derivative of sine x is cos x. Okay, this is provided x is measured in radians. It's never really going to be an issue. Okay, but that's why we did that in radians. Okay, and we could, if we did the same process, I could do exactly the same thing again. What we find is that the derivative of cos x is minus sine x. Okay, when we bring a k constant in, okay, when we basically bring a coefficient in, it doesn't actually change anything at all. In which case you have these values. These are the values given in the little table in your formula sheet. So again, you don't need to memorize these. It's just showing you where they actually come from. Okay. So if your function is y equals k sine x, the derivative will equal y equals k cos x. If your function is y equals k cos x, then the derivative would be y equals, or dy by dx equals minus k sine x. Okay. Obviously, there's questions around about this. So let's look at some of them now. Okay, so examples differentiate the following with respect to x. We've got sine x. Okay, so we're saying y equals 7 sine x for the first one, in which case, using the table, the derivative of sine x is cos x. It's as simple as that. Dy by dx is 7 cos x. Okay, so the only difficulty comes when we're differentiating cos x. Okay, but it's virtually the same. Y equals 3 cos x, the derivative will be minus 3 sine x. Okay. And then just be careful if you've got negatives and things. What if y equals minus a fifth cos x, then the derivative would be minus a fifth sine x, which is obviously just positive a fifth sine x. It is literally as simple as that. You've just got to know, obviously, to use the table that's in your formula sheet. Okay. Right, obviously we could put these in a context. So this is just kind of combining the two previous lessons that we've done. We want to find the gradient of the tangent to the curve y equals 3 sine x at the point where x equals pi over 4. Okay, so same kind of idea as before. We're going to differentiate first and then substitute in that value. So if y equals 3 sine x, the derivative dy by dx equals 3 cos x. And at the point where x equals pi over 4, then the gradient will equal 3 cos pi over 4. So substituting into the derivative, 3 cos pi over 4. Pi over 4 is obviously 45 degrees. Cos pi over 4, or cos 45, is 1 over root 2. So 3 times by 1 over root 2 is 3 over root 2.